So, okay, hello. I'm Daniel Mende, that's Simon Rich, and we would like to tell you something new about botnets. We discovered some new techniques, or maybe we got some interesting thoughts about. And first of all, little notice, you can read it your own. It's just for legal compliance. Okay. Who we are? We are working for a German-based security company called ERNW. We're fiddling around with hardware and protocols and all the OZ layer stuff for a few years, and we have implemented some new techniques. We get into layer 2 fuzzing and some of this. Okay, let's have a look at the agenda for today. The first point, we will point out some Botnet basics just to get you into the stuff and let you know what we're talking about. Okay, so the next 3 points are the topics. So we want to show you how to perform a DDoS attack without OS compromisation, so the host will be untouched. We'll just abuse it. There will be a demo too. Okay, then we have some, or we abuse some new protocols to build up a nearly untraceable or untrackable botmaster communication structure. And at the end, we show you something we implemented to get a bot to master channel. It's a tool. It's not productive yet, so we won't release it actually, but it will be released in the future. It's just a botnet study about what you can do today and what you can do in the future. Okay, after that we will get some conclusions on this topic, and that's it. Okay, so Simon, will you get into the stuff?
Hi. First of all, I want to show a little bit, talk a little bit about what is a bot. A bot is some kind of malware, spam, or perform some malicious action. Typically, there are 4 phases for a bot. The initial infection, the contact to the bot master, and download the payload. The initial infection can be in many different ways. You click on your greeting card.exe and in the mail attachment, and you get infected. You need a communication channel between the bot master and the bot, so that you can, in the next step, send from the bot master that you can send payload instructions and stuff to perform actually the action, the malicious action for which is be done by the drones, the infected systems here. Can be what is to be done. Can be many things like recruiting new bots, relaying of spam, distributed denial of servers, or just click on paid advertisement banners. This is what a bot generally, high level. Just for your information, what's fast plug? You need communication between your bot and your master, and it should be traceable. If it is a fixed IP address, for example, you just blacklist the bot master, and there will be no communication channel. So the bot master always want to be not traceable. So there comes DNS in it, and they just a name for a short period of time. Here, for example, 10 minutes, and it's the host name is calculated via algorithm. The drones know this algorithm, so they can trace, can contact the bot master, and only they know the actual name. Because, for example, there was a date in it, so that for the time, so that every 10 minutes you change it. It can be done in many ways. You can use crypto here to make a hash over time and a specified name, and there is this you use as your DNS name to contact your botmaster. And then the blacklisting won't work anymore. So
okay.
I think it's enough of the basics. Now we're gonna go to our interesting stuff.
That was a really fast introduction.
I know.
So, okay. Now we will look at our first topic, how to do such attacks without touching the operating system. So we won't compromise the operating system. That means we can't or we needn't to deploy a client component. That get us some plus points, but it makes the thing a little bit different. And we have no need for a communication infrastructure. There is no client component. We don't have to tell the client what he should do, because there is no client. So we don't need any fast flux or hidden communication channels or stuff like that. Okay. What we do is we abuse some flawed protocols. Okay, you surely remember SNMP. SNMP is a really, what should I say, a crap protocol? I don't know. Okay, in SNMP there are many, no, not many, there's one well-known vulnerability. It's all about the communities. The communities are like passwords for SNMP requests, and they're in version 1, in version 2, and the mainly used version 2C are transmitted in clear text. So if you sniff an SNMP packet, automatically you get the password. That's one point. The other point is that these communities have well-known defaults. I think about 50% of all SNMP-speaking devices got these two communities, public for read-only access and private for read-write access. So that's what we're basing on. There is another fact that we abuse. This is SNMP is UDP-based. So spoofing the source address is no problem. If we had TCP, we have to figure around with the handshake and stuff like this, but we are UDP-based, we just fire out packets. So that's what we'll do. Another point is that most of SNMP-speaking devices don't log fail accesses, which means we could brute force. We can just scan whole networks. If we don't got the right community string, no one will see that. Okay, and SNMP is used for network management. That means it's really down in the layers. So the most companies won't ever change their SNMP passwords. That means once you got it, you can abuse it every time. Okay. A point to SNMP v3. There is a secure version of SNMP, which is v3, but I don't really know a big company who uses SNMP v3. This is based on laziness, but SNMP v3 isn't supported by the big vendors too. So like Cisco Works or HP OpenView, they don't support SNMP v3 really good. So why? The first point is the architecture of the MIP structures and stuff like that is a little bit different from previous versions, and there are some design weaknesses in the SNMP. For example, on a Cisco device, you don't even will see the SNMP configuration in your system conf. So if you make a show running config, you won't see that SNMP v3 is configured. This is part of the architecture from SNMP v3, but it's make the work very, very hard. Okay, and all security companies say, hey, use SNMP v3. Use SNMP v3, but there is one more problem. Have you heard of this? There was an authentication bypass vulnerability in SNMP v3 based on the 10th of July this year. So, a little bit detailed, it's about the authentication mechanism SNMP v3 uses. It's an HMAC, and this HMAC got a variable size. So now you can speak to your SNMP v3 device and say, hey, I'm gonna authenticate with an HMAC of 1 byte. And you know, 1 byte is, to brute force, is just 1 byte, yeah. Okay, so if you have adhered to your CIO and deployed SNMP v3, you got fucked. Okay, we did some scanning in the internet to do statistics. We did this last year in, I don't know, January, February, something like that. And we scanned whole internet ranges and pinged devices. And from 230,000 devices that are answering on a ping, there are around 16,000 SNMP speaking devices which answers on an SNMP public community string. So this is 1 out of 15. And even there are 700 or about 700 SNMP speaking devices answering on the community string private, which didn't automatically means that we got write access, but in most cases we got. Okay, if we got these counts, if you think about 350 million alive nodes in the internet, that makes 1 million private SNMP devices out there, just waiting for be abused. Okay, I will show you some findings. We made scans about square 8 networks, and in one of this network we found some extreme devices. There were we didn't scan the whole square 8, but in I don't know, maybe say it's a square 16, we found about 460 extreme devices, mainly big Summit or Alpines. Alpine were 83. So if the Alpine 3804 didn't say you anything, where's my slide? No. I lost my slide. Damn it.
Yeah, the extreme summits are...
Wait, I got it. No. Hey, that isn't fair.
The problem with the extreme devices is that there are shipped with SNMP public-private and it's enabled by default. So if the administrator doesn't touch it,
so here are your bots. You see these big networking devices, which are the big Alpines from Extreme Network, sitting around in the internet with SNMP private enabled, just waiting for be abused. Okay, so now I have to switch back to the other version of the presentation. I'm sorry for that. Somebody had stolen my slide. Okay. So you see, there are quite big boxes, and these big boxes are not connected via DSL or something. They're sitting in the backbone. So they got big bandwidth and got really much power to shoot. Okay, we'll show you a short demo. So I got prepared.
I just want to say something about this SNMP slide. Then we would see the boxes and the target and you as the attacker.
So, okay, that's me. That's my attacking system. I'm gonna execute here some Perl script I wrote 1 year ago and improved by the time. This script is gonna send out. Wait, maybe the slide is good. This script will send out these red lines are my SNMP requests. I send an SNMP request with a faked source address. You remember it's UDP, so it's no problem to fake the source address. And I send these packages with the source address of my target. That means that that device answers my SNMP request, but didn't send the answer to me, but to the target. Now I optimized this mechanism in a way that my outgoing packets are as small as they can, and the answering packages on the target side are as big as possible. Sometimes I even get the full MTU. Okay, that means we are playing a little bit an amplification attack. So I send out very much small packages, and the target gets all the packages down. And so we're playing in DDoS. Okay.
Can you please, for the demo, turn off the camera? You can turn it on again after that.
An untraceable bot to master communication infrastructure. Go on.
So, using someone else's infrastructure, cool point of that is that you don't have to deploy your own infrastructure, someone else is doing it. That's really correct. So, Microsoft got a whole bunch of new tricky peer-to-peer protocols. They're coming with Vista and with 2008, and will be going on the later. In case for the IPv6 integration to make a protocol for the years where there's IPv4 and IPv6 on the network, they have to interact. There's Teredo. Who knows Teredo here? Okay. There are others like local, for example, PNP. We will see Toledo is the building up. You only have IP version 4 connection, and you need to reach IP version 6 also. There are many different, like 604 and 46. But Toledo has built-in part which connects to this Tumble server, and you build out a tongue, and there you have a real IP version 6 address, which is reachable from the internet directly. So this even works through NAT. So UDP, there's still the tongue, you'll see. And with this IP version 6 address, the rest of the protocols can begin to work. They need version 6 address. So short picture for Toledo. It's UDP based to make holes in the firewall, because if you have a stable firewall, UDP will close support after the connection is ended, and UDP it's just a timer in your NAT device when it gets closed. First of all, you build up your Toledo server, then you get your IP address, and then you send bubble packets out that the Toledo server, that is ensured that the Toledo server can always reach you. So, for example, if you want to communicate with this one, you send a packet, a Toledo packet here to this box, and it will fail because here there is no net entrance. But now here is the outgoing net entrance for this, so this box can theoretically answer it. So the Toledo client knows that this packet will fail potentially, and sends an exit to the Toledo server with the old address and port stuff in it. This Toledo server knows this Toledo client can send it because he has a hole in the NAT. Sends it here, and now this client can send it to here, because here it is also open, because the first initial packet got here, the information is name resolution protocol. It's made for, now you have IP connectivity, now you want to have names. Sorry, this trigger checkpoint was good for that. So the PNIP is distributed name resolution. It works with distributed cache head. It doesn't need a central server at all. It uses at the moment, but it doesn't need it. It provides for the name resolution with dynamic context where you can register names and unregister names again. It requires you can yourself from the MCN block. The central server from MS is needed for the used for the initial finding of your cloud or for your part in distributed hash table where you have to ask because it's all peer-to-peer based, so you ask other Windows boxes for names and where to get these names. But there is no need for central. So, PNP fast plug. So
now it gets interesting.
Now it gets interesting. Yeah, we use the .NET API. Our drones have a salt. In the salt, through the salt they add a timestamp, whatever. Then you have something dynamically based. We build triple algorithm over hash, and we register that go to that name. So the botmaster register that name, and the drones use this name to connect to the botmaster. And they register every 10 or 15 minutes. You can code it like you want. To register that name and to building up your name resolution infrastructure. All this resource we have PNP all over the stereo stuff, so it's nearly untraceable because it goes through NAT, so you get an end user at home, and also companies use NAT. Yeah, this is what it's about PNP. We coded it with the .NET framework, all framework functions, so you don't have to be need of some use that you apply. You just use the .NET API like it's done. There's also an extended payload in PNP where you can have 4K data on it. When it gets resolved, the data gets transmitted. It would be perfect for hitting communication channel, so you can use it for fast flux for naming stuff, but you can also use it maybe for the complete communication when you resolve it. We haven't implemented that, but maybe this will be not there. So to use this registration infrastructure in PNP. Now you got scared. You're post reachable from the internet direct via IP version 6 or direct via name, even behind your NAT. I think most people don't expect that at all. And Later and PNP are enabled by default on this stuff. There's just the edge traversal must be allowed in firewall. But what is edge traversal? So here, this is the command for your visa to show if you're communicating with strange names or if you have registered.
Okay, that's my part again. It's the third part, the hidden bot communication channel. So we called this project Project ET. This is where the nice picture came from. ET is the code name for an internal botnet study. We just want to explore new ways to did some bot-to-bot master communication, and it was planned as an environmental testing tool, so that the customer can get the client from you, got a nice GUI, and did some click and see, okay, do DNS channel is open, the PNRP channel is open, and stuff like that. So it's called ET because it really phones home. Okay. The goal of this project was to get a bidirectional communication channel that works even through firewalls and behind proxies. So we used the few open holes left, even in your firewall rules or in your HTTP proxy. We choose to implement at first a communication channel via DNS lookup and the dedicated HTTP proxies. So it should be run on every or most Windows machines. That were the goals. So what we did, okay, the source is written in C#. We used the .NET framework 2.0. 2.0 because this is included in Vista per default and also installed on almost every XP. Okay, it's distributed in two parts. As I said, it's a client component and a server component. And I'm sorry, but it's not yet in a productive state. It's still heavy under development, so it wouldn't make sense to release it now, but we will release it in the future, and we're just gonna tell about. Okay, so let's have a look at the client component. This client got a graphical user interface just because it was designed to get in the hand of the customer, and the customer don't want a dirty black box that just phones home and maybe copies all your passwords or stuff like that. He wants to know what's going on. So we implemented a GUI with colorful buttons, and so the end user can click on it and see if some channel goes out. Okay, we only use high frequently used system calls to get our communication done because actually we are playing in a bot scenario, so we want to hide our communication. We don't want to use a raw socket or stuff like this. For example, the DNS communication channel on the client side only needs one system.net.dns.getHostEntry call. This is just the .NET method to resolve DNS hostname, and this is the only system call it needs. Okay, that's a short screenshot of the client component. So you got the DNS test, and you see the test started up. After that, it tried to reach the server. If it reached the server, it just fall into a polling thread. You will see later on why. And sleeps for a server given time. After that time, it pulls again and will get a sleep command. So we could just inject other commands here. Okay. Now, let's have a look on the server component. The server implements an pseudo DNS and HTTP server, which means it looks like a DNS or an HTTP server for the whole internet, but it didn't implement the real DNS or HTTP functionality. It's just an endpoint of the communication flow. We just want to get packets to that machine. The server component includes an GUI interface too, to visualize the connected clients and to interact with that clients, to send commands to them, to, I don't know, to sleep, to execute some shell command, to upload some bytecode or stuff like this. Okay. This is the first screenshot of the running server. This is just a console output. In this case, you see the one drone just sent an sysinfo, you know, system info on the command line. This is that. Okay, this is the log window. You got a window for all the connected clients, where you see we choose an 1-byte client identification number, and you see which clients are connected. They're partially not connected, but they send packets. Okay. We also got some kind of state machine included that all the clients, it's a bot scenario. What should a bot do? In the first case, gather system information. So state 1 is do an system info, send me the output. State 2 is do an if config, send me the output. State 3 is, I don't know, do something else, send me the output. State 4 is receive some bytecode, and state 6 is execute it. Think about something like that. Okay, now I want to go into deep in the two communication channels. First of all, let's have a look on the DNS channel. The DNS channel is nothing new. Since days, everyone tunnels everything through DNS. So you can think we just invented the wheel for the second time, but it is still possible even in big company networks. That is what it makes so interesting. Okay, we need a bidirectional communication. So we need to send data to the server, and we need to receive data from the server. Our way home is to resolve a host name. That's what DNS is made for, and the host name is something like that, datbeef.test.enw.de. Your server component needs to run on a server which is registered at the name server for the appropriated subdomain. In this case, it's test.enw.de. He must be registered because otherwise he won't get the packages for questions to this subdomain. The actually data is hidden in the host name which is resolved. In this case, it's datbeef. Okay, so the server gets your data, you resolve a host name, and that's your way out of the company network. It's the way, one way. Okay, and after that, the server will answer your request, but we will see shortly. Okay, this is a screenshot from Wireshark, and it shows just an DNS query. In this case, I resolved datbeef.test.enw.de, and I just put in this screenshot to show you that you got much of overhead in this scenario. So we actually transmitted 8 bytes, and we got a really big packet going through the cable. So you got really much overhead. That means you won't get a fast connection, you won't get a low latency connection, but it's a way out. Okay, the way back in to complete your bidirectional communication channel is the answer packet to the appropriated DNS request. So your server component gets the DNS request, and he seems to be in DNS server for the outside world, but he isn't really in DNS server. He just get the data string, you submitted it, and put it into the state machine, into the backend. Look, which client just sent us some traffic? What did the client want with the traffic? Is it just a new client spawning up and registering, or is it some packet out of a data communication? Okay, so this state machine then generates an DNS answer package and encodes the data back to the client in this DNS answer. Okay, I got here a DNS answer package. I was lazy, I just took one Google. Okay, first of all, you see in an answer package you can get a whole number of answers. If you resolve a host name, you will not get one IP address, but you will get 2, 3, or 4 IP addresses. So, but in these answers, there are only one little field, the address field, that we could use for the communication channel. Why? Because our API that we use, the .NET API, takes, this is the function call I showed you before, the resolve name blah, and it takes a host name as argument, and it will deliver you a structure of IP addresses. So you just get this little field. And you see, in this case, we get only 4 bytes, or if you send more answers, you get 4 bytes per answer. And this means you get even more overhead on the way back in. But it is a way back in, remember. Okay. So, on the DNS channel, your code will have to watch some details, which are the requests don't get to the server in the right order. Think about some DNS resolve latency, or maybe you handle over the request to another server who did a recursive lookup and something like that. That means you get in a data transfer, you get all the packets mixed up. That's why we implemented a byte a number. We're just increasing by 1 with every packet. So we see, okay, first this packet, then another, and so on. Okay, you will have to disallow the caching of the names you resolve, because it could be possible that one client resolves the same name than another client, but the server will answer it with other data. But if some DNS server in your lookup way will cache the information, this is why the client will get the wrong answer. Okay, and there is one more we have to look for. Your DNS packages shouldn't get bigger than 512 bytes, because in the RFC it's written down that DNS requests and answers with more than 512 bytes will be transported over TCP, which means they were blocked by a firewall. Okay, in our test environmental, we just fiddle around a little bit with the different values and found that we can actually send about 24 bytes per request. That's not much. Think about, you got an MTU of 24 bytes. It's not a good line. Okay. Now have a look at the HTTP channel. It works almost like the DNS channel. You got a request. You request some URL, like here in w.de/test/deadbeef, or you use an CGI and encode the data in the parameter you handle over. So you're open to both. And the answer will be held in the HTTP body from the server. So this method even goes through proxies. This communication channel isn't implemented yet. I'm just on fiddling around with it, so that's why the whole system is not in a productive state. Okay, we got some problems on the HTTP channel. First is finding the proxy. This is kind of really easy. You just have to read the Windows system configuration. And think about, you're in a .NET environment, so you have nearly full access to the whole Windows system. We can, thanks to .NET, spawn an instance of an Internet Explorer object. This Internet Explorer object will get all the privileges the user it executes, and so we can abuse cached proxy authentication. Okay, and even if the proxy requires an NTLM authentication, we could use the logged in user context to avoid this. Okay. One point about the data encoding. We're actually using base 64 encoding for the HTTP channel and base 32 encoding for the DNS channel. We had to use base 32 encoding for DNS because domain name isn't case sensitive. Okay, and why do we encode the data? It's because both protocols are ASCII-based, which means if you got an application layer firewall filtering your HTTP stream and will see binary content into your HTTP request, it should drop the packet. Okay, so we need to encode all the data to ASCII. Okay, there are still some problems left. Both DNS and HTTP are user-initiated protocols. That means, on DNS, your client has to resolve a host name to receive data, and on the HTTP channel, you have to request a web page to receive data. That means your client needs to implement some polling mechanism. You saw it on the screenshot of the client that it goes into a polling loop and polls the server in a randomly chosen interval for updates. Okay. Some future goals is we got a file transfer mechanism implemented. Future goals are to finish the HTTP channel and to improve this file transfer mechanism. And after that, you can think about all the evil botnet functions like dynamic bytecode distribution and execution. Okay. So .NET is really a botnet. Okay. Now, we were really fast, thanks to Simon. Okay. Let's have a look on the conclusion slides and maybe get some beer. Okay, thank you. Okay, so on the end we can say there are lots of old protocols, lots of flawed protocols, which can be abused in a way that most people didn't expect. So think about DNS. DNS wasn't implemented or
it wasn't designed and implemented with security in mind when it was invented.
Yeah,
that's
and
why we have these problems today. I think everybody knows.
And it wasn't implemented to actually file transfer over this protocol. It was invented to resolve host names, to resolve IP addresses. Okay, so these protocols are really old and designed without security in mind. And so the best way to get around these problems is to isolate or to replace these protocols. So think about SNMP. It's the same thing. Replace it with SNMP v3. Okay, you got this very ugly SNMP v3 bug, but okay, you will have to live with. But then isolate the protocols. Do an own VLAN for SNMP. Do a management VLAN for SNMP, and you won't get in trouble. Your devices won't take SNMP packages from outside of the VLAN, and you don't get in trouble.
There are many ways to fiddle around these SNMP, but you should not listen on a public reachable interface for SNMP because it's not necessary. It's just because of the laziness of the configuration why this box is out there and these whole much boxes. That's all.
Okay, and some other conclusions. There are not only old protocols, but new protocols too got spawned up very fast. So think about Vista. With Vista, there come so much new protocols MS invented, and they're really cool protocols. So they're
working really good. This PNIP stuff, we coded it and we tested it, and you can really reach it from almost everywhere. Your box at home behind your your DSL, and you can reach it from everywhere. I didn't find an internet exit where it doesn't work. This PNIP stuff always find a way out. It's not always, but I wasn't in a solution where it doesn't work.
Okay, but this means it's a very mighty API, your .NET environment, And you don't have to invent the wheel twice. Just use the API calls, use that rock-solid protocols. It's cool. It makes your bot smaller and even more powerful. And of course, .NET is bytecode interpreted, so you got this really cool dynamic code distribution and execution. It works on every hardware platform, so.
We didn't test it with Mono.
Yeah. So this is really hot stuff. Okay, are there any questions?
Yeah, please.
Okay, that might be an option. Okay, so your first question. We choose to use .NET and the .NET API because we want to run this, this environmental testing tool on just every company.
On the customer side, to test for that, to test them if they can test their boxes, if they can go out. And it's really common that .NET is installed with Vista. There's default, and you don't have to install so much things on it.
Yeah, maybe you can install software. Also, no, you don't. You just need to execute it.
Yeah, but there's no language where it's so easy to use the Internet Explorer object and all these things to read the proxy, to even the authentication on the proxy and all this stuff, where it works that easy. This is why we choose it initially. Simple.
Yeah, it's simple, of course.
Sure,
C#.
You can program it in Python or whatever, but then you need a Python environment and all this stuff. If you program it in C, for sure you can also use the Microsoft API.
With Vista, .NET 2.0 comes out of the box. Okay. Yeah. Yeah, we actually got an fast flux name registration part, and we did an echo server within the fast flux network. We didn't bring this to the ET project, but for the talk, we just want to get a little bit into the thematic, and we coded in fast flux client in PNP, yes.
You don't need to code all this Teredo stuff and so on.
Yeah, just use the API.
You just use the .NET API.
It's about, I don't know, it's 150 lines code.
Yeah.
It's really small.
The name. It's one of these Windows Communication Foundation channels, and you just register a name with PNP name, and all the stuff gets done for you. You don't have to code Teredo. You don't have to code PNP. You just have to really to implement your client logic. To use it as an hash algorithm, to use the time, to read the time, get the time object, and do the stuff, and use a solve, for example, whatever. So there was.
Okay. Yeah, please. Sorry, why we don't use other records? Yeah. Yeah, it's because our testing in environmental is an IPv4 network, and most company-based, company internal DNS server are IPv4 based too. So if we want to test it in a company space, we have to use the common used mechanisms. Yeah.
Maybe that's an option if we had that, because there's so many things would go to our mind to implement, and we just haven't. We just have done the basic things to test if they work, and the DNS stuff is working the most of the part, and this PNP stuff is working. And maybe in the future we integrate it, and for sure this is a good idea if it works.
Okay, there was another question.
One last question. Why just limit yourself to A or what a record when you produce? Why did you just try TXT record, for example, and have a less overhead and more provision?
A good hardened company DNS server won't resolve TXT records. That's the case. So, okay. Any more? Okay, up there.
What's your application ratio for the SNMP?
What is, sorry?
The application ratio.
Oh, okay. We made, that is another slide that was missing. I can show you that.
Where are the slides?
I don't know. Maybe I left them yesterday in the pub.
Yeah.
So, okay, it's this one. Okay, it was, I did it, told it to you, so we got the request package, which got about 60 bytes, and as I said, the answer packet can fill up the MTU, so in our test environmental, we made it to generate with a 2 Mbit upstream up to 50 Mbit downstream on the victim size. So you got a ratio of 25. Okay.
Any more questions?
Any more? So we just want to thank Federico and Francisco to inviting us. So thank you. And we want especially thank Dominic Bayer for pushing us onto PNP. And for sure, we want to thank all of you for being here and listening for us. So thanks for your attention.